Welcome back, friends. We are working on the Minesweeper project from the YByte Python curriculum available at www.ybyte.in. We are now looking at a very interesting function, which is being called recursively on those squares which do not have any mines as neighbors. So when we click on that square, we know that the entire field opens up, and we know that we discussed that in the last video, that it's going to happen through recursion by this function called open up, for which we created like a template, like a first order template to set up the recursion. But clearly, this code is presently not usable because notice that there is no way the recursion stops, and any recursion must have a base case, must have a case where we stop the recursion, and that's what we are going to look at in this video. So really, there are two considerations to think about. Number one, we need to continue, let's say, looking at more neighbors, continue searching until we find a non-zero neighbor square. Now, one thing to realize is that the way the game is designed, we will never hit a mine as we search. Now, let me just explain to you what I mean by this. Recall in this example, let's say we look on the right side. So if I click on this square, basically I need to keep going until I hit this particular square. Because of the way the game is, before a mine, there will always be a square which tells that, okay, look, I have something in my neighborhood. So that's what I meant, that I will never hit the mine directly. There will always be this square. And once I hit the square, I will have to stop. So that's sort of like consideration number one, which we must keep in mind when we make the, let's say, make the, base case. The next thing to realize is we want to make sure that the search does not end up in an infinite loop. Now, this is actually quite interesting. Infinite loops can occur even though we put a stopping condition, like, we are saying stop at the, let's say, at the non-zero square. Infinite loops can still occur because every square is also its neighbor's neighbor. So if we do not explicitly prevent this, the search will get into a self-referencing loop. Let me again try to explain this from here. You notice now, to make this more clear from here, let's say I click on this square. As we discussed, we are going to, because the square is empty, the square is a zero field cell, we will ask for the neighbors to do the same. Now we tell the neighbor to look into its neighborhood, but then the problem is that one of the neighbors is also this square, which means that we are in a perilous situation here. I call you to check, if you are empty, you call me to check if you are empty. And we are in this, let's say, infinite loop forever. So we got to also, attend to this situation. In fact, we will consider both these conditions as we, build the program. The first one will be by looking at what's actually on the field list. The second one will be by just disabling a button once it has been visited. Taken together, both will do the job, as we will see later. So let's first look at consideration number one. Let's think of it as sort of base case one, basically saying that, we will no longer call the recursive function if the square on which we are calling it has a non-zero value. So which means that I'm going to put this, remember, this is the code that I have in there right now. I'm going to put this in a condition that, look, if I, search you, if I find that, this field is zero, if this square is, let's say, a zero cell, then I call a recursive call. If I, on the other hand, have a cell which is a square which has some neighbors, I no longer call this recursion. In fact, I just disable, the cell. Of course, I must disable it. That's important. But I just display, like, like in the case of non-zero square, I just display how many mines do I have on this. So notice no more recursion happens here. Let's just go and so I get to my code over here. Now this is all in the function open up. Remember previously we just have a sort of like outline. So, we will have to expand this a little bit. I'm going to say that, look, if my field, say RC at this row column is not, is, sorry, is, let's say, equal to 0, which means that if I have a no neighbor cell, well, then I will find the neighbors, and all these neighbors I will continue to do my recursion. On the other hand, if my field is, let's say, a non-zero cell, which means the zero condition is not correct. If it's a non-zero cell, so I just write that non-zero square. Basically it means that, look, I'm reaching a boundary. I'm reaching one of those edges where there's a non-zero, value now. all I have to do really is that I have to just do exactly, in fact, just this. So basically, I will say, look, display the value of that number in the right color. And that's exactly same as basically as though I went and clicked on that particular button. So this is the sort of the case number one. Now here there is something quite important to understand, which can be a little bit confusing. You notice that I first call this function open up on, let's say, a square which is empty, which means by definition, by the way the code is set up, in fact, this is always correct. But then if that is the case, why is it that we are having to check for this condition once again inside the function? What I mean is that notice inside the on click, I get to the open up only when field RC is 0. If that is the case, then why do I further need to check this? Well, the point is that even though I start my recursion on an empty square, as the recursion progresses, in fact, I may end up hitting a square which is not empty, which is why I need to check for this condition once again, just to make this clear. For example, I start the process here. So say just let's say I just go on the right side. I look at this square. I look at this square. When I look at this square's neighbor, now I notice that there's a square which is not empty. So when I come to this square, which is 1, I will no longer call recursion, and hence the recursive, let's say, the process will stop and I will not go further from here. That's the point. That's the reason I need to check for that condition. Even though the process started on an empty square, it has now reached a square which has got a value. Now, moving on to the second consideration, remember we want to make sure that we do not create an infinite loop. The idea is actually quite simple. I can just say that, okay, look, once a square has been visited, let me disable it, because, what I can then do is that if the square is disabled, then I will just immediately return. I will not cause a recursive call once again. In fact, this is logical because think about it. Every time a square is clicked, a button is clicked, in fact, we also disable it, which means that we are just viewing opening up as another way of clicking. So, the recursive process opens the cell up, but it must get disabled. And like I said, once it's disabled, we can just prevent anything else from happening. So let's incorporate this in the code as well. I get back to my code, open up over here. So what I do is that I say, okay, look, the moment a particular, let's say, a particular square is visited, I am going to disable it. In fact, I will just use this exact code. Now, again, think through this very carefully. This is now happening inside the open up function, which means the moment I call recursion on a particular square, it will in fact immediately get disabled. Furthermore, I do not want any more recursion to be happening from here. In fact, I don't want anything to be happening from this particular square. So I just go and put a condition. Look, if say, if this is the case, so basically I just go and say, if let's say buttons RC state is disabled, if that is the case, well, don't move further, just go back, right? So just let's say go back, I can use a return statement. Remember, return can be used to, prematurely return from a function, and that is quite powerful in this kind of scenario. So, basically that is about the code. So, that's kind of what we need. Now, when I run this piece of code, so, let me just start opening up this mine. Notice I clicked on this. I was quite lucky to have found an empty square, a 0 square. The field opened up quite nicely. Let me try the other corner as well. Wow, amazing. So, this square was empty. In fact, recursively, I have opened up all of this, and you see the result in front of you. Notice all the edges here are in fact numbers because recursion stops there. Also, when I come to let's say a cell of this sort, right? Now, notice I have reached here through a recursive process. All its neighbors are inside, which means that there are no more to be searched. They're all already disabled. So none of these neighbors further create a, let's say, recursive situation. And that's why the recursion remains controlled. Let's try again. Wow, this is really amazing. Yeah? With this, in fact, we can think of really, let's say, solving the puzzle. So let's just once again try to think about what is going on. Let's say I have a situation of this sort where I happen to click this orange square. Remember, the moment I click an orange square, which is 0, So it is going to trigger a recursion. It's going to say basically, well, look at all my neighbors. Now in this situation, these three neighbors are the, let's say, the edges. So basically these three will no longer do any recursion. However, they will get disabled, and let's say they will display the number. But now let's think about it. Let's look at this square's neighborhood. So I'm looking at this square. I've kind of zoomed it out here. Basically, notice in this square's neighborhood, I have got two ones. So yes, recursion will continue. However, recursion will stop here. Interestingly and importantly, on these three neighbors. So notice this square has in fact five neighbors which are listed here, but three of them have already been disabled because they were called as part of the original recursion. So when I run this, so these three will have no impact whatsoever. They won't propagate the recursion further. These two will open up, and the game, that's how we'll open it up, right? So just think about it a little bit. Very, very, very interesting how the code is actually proceeding, and also how it's being prevented from, let's say, just creating some kind of an infinite loop. Very happy to discuss in case you have any questions on this, but I think this is really, really, really interesting. Now, just before I wrap this up, a food for thought is in order here. Is recursion an overkill for this problem? Now, let's think about this a little bit. If there was only a one-dimensional problem, in fact, I would argue that we could have managed without a recursion. We could have done a while loop or a for loop, because all we needed is to search in, let's say, two directions. Let me, illustrate what I mean. So, for instance, let's say in this situation, I could have a code. I just say, okay, look, I have been clicked here. I will run a while loop. I'll go in this direction and find out, keep opening the squares until I find, let's say, a numbered square, in this case, 1. Likewise, I'll go in the other direction and open up all the squares until I find a numbered square, or let's say I'm at the edge of the, let's say, the field. Now, this was okay in one dimension. But think about it. Now we are looking at a two-dimensional scenario from any square. For example, this square, there are multiple directions to go into. For instance, I have to go, let's say, in all my neighbors. So it's basically this, right, up, left, down, diagonally right. So diagonally left. Now, furthermore, I need to go in multiple directions from them as well. And and notice sometimes the shape that opens up like it has happened is really, really quite interesting. Writing a for loop or a while loop for this, I think, will be kind of unwieldy. And hence, I think recursion has provided us a very concise, really interesting, very thought-provoking solution, a very, very elegant solution. And it has done the job without getting unwieldy code. Obviously, we have to be careful. We have to make sure that the base cases are defined correctly, and we have to understand the problem very clearly before we can write. I hope you found this interesting. Look at our website www.wipi.in for many more such videos where we analyze code in detail and try to get deep into how things are working so that they become clear and intuitive. Take care. Thank you so much. Bye bye.